We just talked about a first basic strategy for the relay channel, which we called symbol relaying. For this channel, it's for the Gaussian channel, usually it's implemented as amplify forward, so that the signal just amplifies the signal it receives. And I talked about how using just amplification isn't generally the best approach. It's often good to use a nonlinear function. So x2i equals f of y2i minus 1. Now there's also other methods where what you do, rather than this, naturally, you can also choose a certain number of past values if you want. Right? And in fact, this could now be a linear function, for instance, of all past values, right? And you could do a big linear filter. So you could actually, so some people have proposed, some researchers have proposed using linear filters, and so on. Okay, so there's all sorts of alternatives to keep it. The main idea here is that the relay is kept quite simple, right? So you don't want to do too much processing. Okay, but now we'd like to talk about several strategies, 3 strategies in particular, which are not so simple to implement, and they generally require the relay to have, already relatively sophisticated processing. The one method is known as decode forward. So this is what we'll discuss next. So this is a variation of multi-hopping. It was first proposed for relay channels by Cover and El-Gamal. So most of the basic theory for this channel, in its general sense, right, for the general model, was done by Cover and El-Gamal in a paper from around 1978 or 79. Including this strategy as well as the partial decode forward we'll discuss next, and including the compress forward or quantize forward we'll discuss at the end, although since then there have been a variety of variations on these strategies, in particular on the compress forward strategy. I think there have been important, or at least different ways of getting the rates that they motivated. So the idea here is going to be, I'll describe the most general form. The natural thing to do here is multi-hopping, right? You just decode here and then re-encode and send again. We're going to do something a little bit more general, and that's also the idea of this approach. So the idea here is to use something called block Markov. Maybe I won't use quotation marks. Block Markov superposition encoding. Okay, block Markov encoding. So let's take a look at what that is. What we're going to do is we're going to choose a joint distribution, px1, x2. Okay, so the idea here, so there's no auxiliary random variables, which is nice, right? No auxiliary random variables. The idea here is to build up a general correlation between the input and the output. And to accomplish this, this is where we have to use the superposition coding. So the first thing we'll do is generate you'll see, so let's just talk about it. Generate, let's say 2 to the power of nr code words x2n of w. So in doing this, we're somewhere here assuming that, so r is the rate of the actual rate. So somewhere we're assuming here that this message arrives at the relay and is fully decoded there. And to generate the cooperation, we're going to use superposition coding. Okay, so for each to the nr, generate another 2 to the nr. So here we're reusing the rate. Another. Okay, so sorry, via px2, of course. For each x2n w, generate another 2 to the nr code words, but this time, of course, with respect to x1 rather than x2. x1n, and we'll superpose these on. We'll superpose these on top of the. Right, so from x1 tilde, x1n w tilde w, with it, where this also runs over 1 to 2 to the nr, so this runs over 2 to the nr, this one as well, and now we just do it in the usual way using px1 given x2. X1 given x2, and dot given the ith letter, so we do it letter by letter, of course, x2 I w. All I. Right, so if I draw this now, let's start with the first block. Now in the first block, what can the relay transmit? Well, nothing yet, right? So what we'll do is in the very first block of transmission, the relay doesn't know anything yet, so just sends a default index. Okay. Meanwhile, the source node can already transmit something, namely x1n, with the same index so that they're correlated, w1. Okay, so what we're doing here is, for encoding, we split the message into split nr with bnr bits. So we're assuming we have a block of, so what we're going to do is transmit in b blocks. So suppose the message has b times nr bits into smaller messages, w1, w2, all the way up to wb, with 2 to the nr bits each, with nr bits each. And then what we're going to do is we're just going to hop the message through the network. And the way we're going to do that is put the first message here, w1, into the first block. So this here is b equals 1. And then in the second block, we just have, after this block is completed, the relay decodes the message. If it gets it right, it can of course send itself that message in the next block. And meanwhile, the source node assumes the relay has decoded correctly and simply sends the next message. Right? That's the idea. And now we just keep going. B equals 2. So let's do this for 4 blocks just to give examples. It's easy to write now, right? We're just repeating everything. So x1n. Now the relay decodes the second message, sends w2. This guy does w2, w3. w3, and now at the last block, suppose this is the last block, he'll send w3 and then just send a default index, and then we stop. So now the WB using BMSE. Okay, this is where the name block Markov comes from. There's a Markov chain here, right? Markov chain, always with the same statistic, but it's a block Markov chain, right? There's a block Markov chain being developed. Okay? So that's why it's called block Markov's superposition encoding. So this is a very common technique used in a lot of information theory papers that deal with feedback, because with feedback we also have a delay in the system that we try to use, like here we have to delay things to wait until the relay processes, and then we can send in this fashion. Okay, now there's one subtlety that will come up, and let me deal with this now. We're going to do decoding using a special method, namely a sliding window decode. Well, maybe I mention it later. We could leave it, but we'll do decoding using a sliding window decoding method. The reason for that is, of course, I shouldn't try to decode W1 at the receiver here yet, right? Because there's still influence from W1 from the next block. So I should definitely wait until here to decode it. That's natural, right? I mean, especially if there was no direct link here, I definitely have to wait 2 blocks anyway until I decode, right? So what we should definitely wait to decode until here. So let's talk about that, and maybe I'll mention the important thing when I get there. It's a little bit of a subtlety. Okay, so the idea in decoding, so that I think the transmission is clear, right? So we generated the code book, the 2 code books, and the transmission is done in this block Markov fashion. Okay, so what happens in the decoding procedure? So let's talk about the relay decoding. What the relay does is after block B, so by the way, yeah, here B is, in this example, big B is 3, right? And if we look at the overall rate, you'll see it's B over B plus 1 times R, right? So we're actually reducing the rate, right? Because we have 1 block we lose through this process. It's like a pipelining, right? We're doing sort of like a pipelining scheme. But if we make the number of blocks large, you know, that problem goes away, right? So we can get as close as we want. Of course, there is an issue of error propagation here, right? We talked about error propagation. If a mistake is made here in W1, we're going to mess up everything. But again, error propagation through the union bound is something that increases linearly in B, and fortunately, as we increase block length, the error probability can be made to go down exponentially fast. If we could only make it go down linearly fast, we would have a problem potentially, because the error propagation might cause problems, right? But fortunately, error probability can be made exponentially small, so that's okay. Okay, so after block B, the relay tries to find a W B tilde such that, so after block 1, for example, what it's going to try to do is try to find a W1 hat, W1 tilde such that, of course, we get typical sequences. So such that x2n with W hat B minus 1, which is assumed to have been decoded correctly. So assumed correct, assumed equal to. So if we decode correctly in the previous block, then we have the correct value that we're superposing, and that's why that 1 represents that nicely. But you can think of it here too. It's the same idea, right? We assume W1 was decoded correctly, and then we decode W2. So it's always the same idea. And of course, it's trying to find an x1n of W tilde, W hat B minus 1, which it decoded in the previous block, and then WT tilde, and of course its sequence in that block, in block B, is epsilon typical. With respect to px2, x1, it's always the same order, right? x2, x1, y to the 2. Is epsilon, oh, I have that, yes. That's what it tries to find, right? And actually the analysis now is the same as what we did for the broadcast channel, for the multiple access channel. What we see is, as long as this is correct, then x2 and y2 are jointly typical. So our experiment looks like this: x2, y2, we have y2n coming out, we have x2n coming out, which was typical, and we're asking if this was correct, the actual transmitted WB will cause this to be jointly typical, so we'll find it, right? as long as we're testing with respect to the correct statistics. So now we're asking the question, what's the probability that a randomly chosen x happens to be typical, even though it was created from this statistical picture, right? x1, and where this is now independent of y2, even though we're testing to joint dependence. And you know what the answer there is, right? The probability of this happening for incorrect code words is going to be approximately 2 to the minus n I of y2 x1 given x2, right? Exactly the same picture we had before. And how many of those are there? Well, 2 to the power of n r minus 1, right? And so as long as r is less than this, the relay can decode reliably. So we have the first bound on our rates. Okay, so we have our first rate bound, namely at the relay, r2 less than I x1 y2 given x2. And that one should seem quite intuitive, right? That's just the capacity from here to here, you know, averaged over what has been sent, right? So, I mean, in this particular case, you will just need, well, you might have some correlation. So the x2 might be correlated with x2. So we'll look at what the rates look like later. So that's our first bound. Okay, everyone agree with that, given our analysis tools until now? So this brings us to the receiver. Okay, so for the receiver, or sync decoding, I guess. The relay is a receiver too. Maybe I should say destination decoder. Destination receiver. What does it do? Well, after block B, and we'll start with here, starting with B, equal to starting at b equal 2. What should the receiver do? Well, what it wants to do is decode W1, so it's the same idea. So try to find a W tilde, but now with b minus 1, right? Because we're at block 2, so we're looking for W1. We're at end of 2, so we're looking for W1. Such that, and what it would like to do now, what's the best thing for it to do? Well, it's best to test both output sequences, right? So, because there's information about W1 here and here and here, and so in both blocks, so maybe we should do some test across both blocks. What test is the natural one? Well, certainly we want to make this typical with our received sequence, and we assume we decoded the previous one correctly, so we should use that one to our advantage. So what we'll do is we'll choose x1, and the big ones are the ones that are sometimes random, right? So here we'll have WB minus 2, which is assumed correct again, assumed equal to WB minus 2. Then W1 tilde. X2n we should know because we have WB minus 2. Right? And Y3n, element of epsilon typical set of Px1. I'm being very pedantic with writing this all out, but okay, fine. Okay, but we're not just happy with that. We want that to be typical, and we want the next one to be typical too, right? Namely, which ones should we test here? Well, we could try to test both, but the problem is this is going to be interference for us because we don't want to decode W2 yet, and anyway, it's, you know, we'd want to wait until here to decode W2. So we'll have to think about whether that is the best approach or not. But here we'd like to decode W1, so we can only do a test with respect to this, right? If we want just W1, because this creates interference. It's like another code book. Okay, so and at the same time, we want x2nw b minus 1 tilde. Oh, I should have here put wb minus 1. B minus 1 tilde. Y3 in block. This is block B minus 1, and this is block B, to be epsilon typical with respect to P x2, y3. Okay, that's the idea. Okay, so here we're getting an intersection of events, right? And hopefully that intersection will make things more, better, more stringent. Now, how do we analyze the probabilities, the probability of an intersection of two events? Sorry? Oh, that we could try the indicator function thing, but it would be even better if they were independent events, no? So are these independent events? Suppose we look at the case where this is the incorrect chosen code word, and so this one will be random, and this one will be random. Are those independent, that these two are typical? Remember, the two common random variables are this and this. Are they independent? Well, I would be careful. They're both in the same subcode, right? And they were generated together, right? Both of them were generated together. So they may not be independent. It's not nice. Can we make them independent? And the answer is yes. So here's a little bit of a trick, and this is what I wanted to mention. What we're going to do, it seems like overkill, and I think in practice it is overkill to do this, but rather than generating one code book, we'll generate B plus one of them. So for every block, we're going to generate a new random code book. And then we make them independent, right? So let me show you. So this here will be a random code book for block 1. This will be a random code book for block 3, 2, 3, 4. We're going to generate all those code books statistically independently. Okay, throw them. Then same thing here, 1, 2, 3, 4. And now, if you look at what I'm testing against here now B minus 1. And here I'm going to test against B. Now they're definitely independent because they were generated independently. So both events are independent, and I can take a product of two things. Okay, do you see the point? That's why in this experiment where we're just trying to create, find what good rates are, we're generating a lot of code books, right? For every block, we're generating a new one independently. Okay? If we do that, then these two events are independent, which is great, because now I'll get a product. So let's see what happens. What we're going to look at now is the union. We're going to look at a union of two events, right? So a union, so we're looking at the probability of, let's say, event 1 intersection event 2. Which now, since they're independent, becomes a probability of event 1 times probability of event 2. And what's the probability of this event? Well, it's just the usual thing we have, right? So if this is the correct, if the previous decisions were correct, and here I happen to be searching over the correct one, then this is typical, so I'll find it. So the error probability is the probability that one of these that wasn't sent is jointly typical. And here we just have the case where that has to be typical with these two. So all we're going to do, oh, I should be careful. We again have this situation where we're checking x2, but now with y3, right? So x2 is typical with y3, and so is this, because it's coming from the same code book. Right. So we again get a similar result. So here we're going to get the union bound. How many are we testing against? Well, we're testing against overall. I guess I should be careful. I don't want to do this yet. I want to do this. I'll have a union here. So what I'm going to get is the probability of the union over all W tilde not equal to W, right? Because I'm testing only against one of them. So let me write even B minus 1. Of the intersection of two events, right? And so this is less than or equal to the NR minus 1 times the probability of E1 times the probability of E2. And this probability here is 2 to the minus Ni approximately, 2 to the min x1 y3 given x2. And what's the probability of this event? Well, that one's easy, right? It's independent. So we'll get 2 to the n, 2 to the minus n, the mutual information between x2 and y3, right? to the minus n I x2 y3. So I can add up both information. So that's the important insight. I can add up the information from here, which is I x1 y3 given what I know, and here it's I x2 y3. And that so in other words, we're just going to get the bound. This should have been r less than I of x1 x2 y3. Right? That's the rate we get. Okay, so the decode and forward rate, is that clear? Right, so that's where the sliding window picks up one information from here plus another one. That's why we're doing it. So the decode forward rate, RDF, is going to be the max over all joint distributions of the min of I x1 y2 given x2, that's the relay decoding bound, and I x1 x2 y3, that's the receiver decoding bound. That's decode forward rate. Okay, so now there's various comments to make here. First of all, let's look at an alternative decoding method which may not need this random coding over many blocks, and I don't think it does. I have to think about it a little bit, but I don't think it does. Suppose we do something else. What's the best thing the decoder could do if it didn't care about delay? It would collect all blocks and decode them together, right? So let's say we wait until here. Well, suppose we do the following. Let's just decode W3 here in this example just from this one block. What is the rate going to be? Take a look. You're getting both together, right? Because the last one is just a known index. So we directly get mutual information between x1, x2, and y3 in one block. That seems like a little bit of a simpler decoder than the sliding window decoder, right? And this is called backward decoding. So this idea was Franz Willems and Edward van der Merlen came up with this idea. It's sometimes useful to think of doing backward decoding. And then now if I go to the next block, note I don't need the statistical independence across blocks anymore. You see, so there could potentially be some advantage with this approach. However, you pay a price. You have to wait until all the communication blocks are completed, and generally they have to be quite long. You have to wait a long time to make this efficient, right? So there's a trade-off here. Of course, even better would be to decode everything together if you can wait. But the nice thing about sliding window decoding is you can already decode the first piece of the message here, right? So you can do more like a streaming communications. So it depends on how important delay is to you. If you don't care about delay, you can wait until the very end and decode backward, and that simplifies things. Because once we've decoded W3 here, well, now we know W3 and we can just decode W2, right? It's the same situation every time. So that's called backward decoding. It's a little bit conceptually simpler, and I don't even think we need any more. I'm quite sure we don't need the different randomly encoded block codes every block. In fact, I'm pretty sure you don't need it even with sliding window decoding, but just to formally get this through as a product, it simplifies the proof, right? Because we get independence. Okay? Fine. That's one comment. Second comment. How does this compare to multi-hopping? So what would the classic multi-hopping rate look like? So it's worth thinking a little bit about this. So classic multi-hop, wouldn't that get, well, there we're sending to here first, so we would need the rate to be less than the minimum of I x1, y3, say given x2 being 0, being its best value, right? Or any other constant for that matter. And then we would do the next hop, which would be I x2, y3, given x1 equals 0. Would be this, right? So if you compare these two rates, you can clearly, this should be a 2. If you compare these two rates, you can see that you're definitely doing better. This rate is as good. These two rates, this rate is as good as this one, which makes sense, right? In fact, usually this rate is better because we can fix the value. So by doing classic multihop, we can even make this number bigger than the best possible one here in general. However, this rate is a lot lower, potentially, because we're only getting the direct link, right? So this one will drop. And usually you're trying to choose these so they match, right? And since one of them drops, you've made things worse, right? As soon as you make one of them drop. So that's one disadvantage. Now, what's the difference between these two? Well, note there's a few subtle things here. First of all, here we are using coordinated transmission, so we're even if in terms of wireless channels, we're allowed to use beamforming. So the two nodes are acting as a joint array to beamform, right? Which we can't do here. In other words, while this guy transmits, so does this one. Now, another comment here, though, is to accomplish this, of course, we need, the way we've built this here, it's also actually a result for full duplex. It seems to be for full duplex channels. But as I mentioned, I can build into the channel model that whenever x2 is not 0, y2 is 0, right, is a constant. So I can build that into my computations too. So actually this result includes half duplex channels too, of various kinds. Anything else? Any other difference? And of course here the receiver just uses the, doesn't listen during this period and is just decoding after the relay is transmitted, whereas here the receiver is collecting all available information to decode. So there's several different aspects appearing in this problem that didn't, in this method, that don't appear in classic multihopping. In fact, sometimes you find classic multihop is worse than just sending directly. So there's, in particular, if you have a wireless scenario where the attenuation factor is like free space, then this is usually a bad method because you lose a lot of pre-log. So this method is only good if, for example, the transmitter and the receiver are very far isolated from each other, right? So that's the classic way of using a relay, right? It's to do range extension. It's the classic way of doing relaying. And then you doing multi-hop is reasonable. I mean, if nothing gets from here to here, but if the relay, in general, there's still energy going from here to here, and then you should also be using the signal you receive from the first block to help you decode in general. Okay. Any questions? So the main new things are sliding window decoding versus backward decoding, and also the way the method looks. So let's do an example with Gaussian channels. Oh, well, maybe we do one example first for our little, we had two examples we were considering, right? One was the classic network and the other one was our Gaussian model. So let's look at the classic network first. Right, we had we had our wires, right? 1, 2, 3, and let's say, so this is x11, x12, y32, 1, I don't know, 32, y31. Can't remember which way around I did it, doesn't really matter. x2, y2. And suppose the capacities of links are all 1. Then we know the capacity of the relay channel here is 2 because we can do a 2-path routing. One part of the message is routed here, another here. And notice here we're doing no rate splitting, so we're using a different approach. What rate does our decode forward achieve here? Well, here the best approach is to send independent random variables on every link. That's always the best when you have independent links. So you would choose here, you would choose x11, x12, x2 as being independent entropy 1 to get the full amount of information across. And what do we get? What is I, x, What is this one here? Well, this is going to be I of, so we have y2, so I x11, x12, y2, given x2, what is that? Well, here we may as well, only x11 has an influence on y2, right? Because y2 is x11, right? So this here is just 1. Turns out to be just 1. Because the entropy without x11, I don't know whether it's a bit is 0 or 1, but once I know it, the entropy is 0, right? Because this is the entropy of y2 given x2, and the y2 given x11, x2 is 0, right? So here we get 1. So you see already, even whatever we have here, this thing here is less than or equal to 1. Right? So we're actually suboptimal. Why is that? Well, because decode and forward assumes the relay decodes everything. You see? And because I'm forcing the relay to decode everything, I am suboptimal, right? So you see already with this simple example, it's quite important to include rate splitting at some place. So we'll do that with what's called the partial decode forward strategy, where we force the relay in the abstract model to decode only some subset of messages. And once we do that, then we'll recover the capacity equals 2 again, right? That is the capacity. In fact, this number here is 2. Right, because it's going to be the mutual information between these two going to here, and since both are, there's 2 separate links, each will give them information of 1, and then we'll get the number 2. So this is actually 1. That's exactly 1. Okay, clear? Okay, so let's go to the additive white Gaussian noise channel, and we'll study here the full duplex model. Could also to study the half duplex model. That's also interesting. So the additive white Gaussian noise channel, I can write it again. Y2 is x2 plus z2. Oh, let's add geometry. I wanted to add geometries here. So suppose we have the following geometry. So suppose here's the source node, and suppose the relay is on a line between the source and the sink. Well, let me use numbers, 1, 2, 1, 3. And suppose the relay is some distance, d, on the line between the source and the sink. It should be 2. Between the source and the sink, and distance d from that node, and suppose this distance is 1, so that then makes this distance 1 minus d. Okay. Now, if you don't like, distances going to 0, remember back when I first published, at least my paper, I had this geometry, and some people said, "Oh, it doesn't make sense to have a Gaussian channel when the distance goes to 0." I say, yes, I mean this distance 1 isn't meant to be like 1 meter or 1 centimeter. It's just a normalization, right? With which it's a relative number, right? So it's a fraction, but then, anyway, okay. It's the same thing. You sometimes probably, so there was, some of you know like the Gupta-Kumar scaling results. You may have heard of those, very nice results. And they're scaling results as the number of nodes goes up. Of course, at some point the models break down, because if nodes get so close together that you enter the near field, then the models don't make sense, and then the scaling no longer makes sense. But that's not what the model is supposed to study. Of course, you're just studying the case where the model still makes sense and you're getting very large. So it's sort of a, you don't want to go to the ultimate limit where all of space is filled with little network devices, right? Anyway, there's a relative nature to this. Anyway, additive white Gaussian noise with geometry, of course, we'd like to add realistic models, but the model we'll use is just going to be a Gaussian model, which is okay if these distances are of a reasonable size. Relative 1 is just a normalized number. So y2 is going to be what? What this guy received is going to be x1, and let's take free space propagation, right? Free space propagation divides by d. If we had an attenuation factor of 3, then I'd have to here put 3 halves, right? Or if I had an attenuation factor of 5, it would be 5 halves, but here. So this is where it doesn't really make sense to have d go to 0, right? Because now I'm getting more energy at here than I'm even transmitting, right? So that sounds strange, right? it sounds strange to get more energy here than what I put into the system. But again, it's a relative thing, right? So everything is still fine by changing the noise variance. So we're just going to choose the noise variance to be 0, 1, just for simplicity. And Y3 is now going to be, so this is full duplex communications. X1 is divided by 1 plus X2 divided by 1 minus D plus C3. Okay, so that's going to be the model. And now let's look at what we get. What's the natural choice to use for Gaussian channels? Well, of course, it's Gaussian random variables. In fact, here, Gaussian random variables will be the best choice. Why is that? Because here, I can always write this as h, let's say, of y2 given x2, minus 1/2 log of 2 pi e, right? Because the entropy of y2 given x1 and x2 is just the entropy of the noise. And so it becomes an entropy maximization. And since I have a variance constraints, you can also show that conditional entropy is maximized by Gaussians. And the same thing will happen here. And of course, what optimizes both is going to be the same Gaussian because we have a power constraint. So in other words, this max will always have Gaussians in it anyway. For the Gaussian channel, for this simple Gaussian channel. So R df is in fact going to be the max, and now we're allowed to do any joint correlation, so we're optimizing over a correlation coefficient, right, rho. And of course it makes no sense to have negative correlation, because if we have negative correlation we'll reduce the energy at the receiver, so we should only need to optimize over correlation coefficients between 0 and 1 of these two numbers. So now we have to calculate what this is. Okay, so let's go and do that. So what is, well, we just wrote it out, right? What is h of y2 given x2? Well, there's several ways of doing this, but the easiest is just to write this out usually as x2. If you really want to be sure, this is the best way to do it, right? We have that identity, right? And then computing the entropy of the joint is just 1/2 log 2 pi e, the determinant of the covariance matrix between x2 and y2, and so this is just going to be p2, right? Right, so that's one way of doing it. So, of course, if you know how to do it, you can do it a little faster. But so what is this covariance matrix here? Well, it's the P1, right? P2, and then root of P1, P2 rho, root of P1, P2 rho. That's the general form of the covariance matrix. Right? It's the same thing as the correlation matrix, too, because we have 0 mean. The determinant of that is going to be P1 times P2 minus P1 times P2 rho squared divided by P2, so we'll just get, well, P1, P2, 1 minus rho squared, as you're probably accustomed to. So this whole thing is just going to be P1, 1 minus rho squared. So here we'll get log, 1/2 log, for real channels. Of course, usually we want passband, not baseband, but okay. Oh, do I want to do this with, oh, I have variance 1, that's fine. So we get, oh, and I forgot one thing. I forgot the D, right? So there is a D here. So y2, gosh, you should have stopped me. This is the correlation coefficient, covariance matrix x1 and x2. I want x1 and y2, right? So what is x1 and y2? Here I need the power of y2. Let's do this again. This is y2. What's the power of y2? Well, it's over there, right? P1 by d squared plus 1, right? And the correlation between x 2, here I need 2, oh gosh, a lot of mistakes, 2. The correlation between x2 and this, well, is going to be the expectation of x1, x2 divided by d. What's the expectation of x1 and x2? Well, that's going to be, the correlation coefficient is defined as being the expectation divided by root of P1, root of P2. So this is just going to be root of rho, root of P1, P2, divided by D. And same thing over here. Okay, now, if we hopefully got it right, now we have to do the subtraction. So if we now do the determinant, what do we get? We get P2, P1 by D squared plus 1 minus rho squared P1, P2 by D squared, right? So the P2's at the bottoms will cancel these P2, so I'll get P1, 1 minus rho squared over D squared. So it's going to get P1, 1 minus rho squared over D squared. That's the first one, right? And if you look at it, that should make sense, right? If the conditioning on the x2 wasn't there, then it would just be 1 plus P1 over D squared. And we're reducing the power by the how much there is correlation, right? It's 1 minus rho squared. Is that okay for everyone? Okay, so that's the first answer. Now we have to do the second one. The second one will be a little easier because we just have the differential entropy of y3 here, right? It's just h of y3. And what is h of y3? That's just the variance of y3. What's the variance of y3? Well, that's going to be 1/2 log 2 of 1 plus, that's the noise, plus the power, P1 plus P2, 1 minus D squared, plus the 2 times the correlation between the two. So it's just going to be 2 rho root of P1, P2 divided by 1 minus D, right? Okay, so there it is. That's the expression. And the rest we have to optimize over rho. So there's no the choice for rho depends on D, right? So we have to choose an optimization. Nevertheless, we can do some special cases, right? What are the interesting cases? Well, suppose the first one is suppose D approaches 0. So suppose the relay basically lies right on top of the source. What's going to happen? Well, we think that this blows up, right? Does it? Well, sure. So this first term blows up, unless we make rho go to 1. But rho goes to 1 is what we want, isn't it? Because then we'd have perfect beamforming to the receiver, right? So in fact, making D go to 0 lets us make rho go to 1. Okay, so that means we can choose rho going to 1. And then if we look at the second term, what's the rate we will get? Well, it's just going to be 1/2 log of 1 plus, here we'll get 1, right? So we'll get P2, and we'll just get 2, this will go to 1, we get just P1 plus P2 plus the root of P1 plus 2, that's perfect. Beamforming root of P1 plus the root of P2 all squared, right? That's what we'll get. And that's just the full alignment. It's like a maximal ratio beamforming, if you like. And of course, we can't do better than that. Because, and it sort of makes sense. If this guy's right on top, we basically have a two transmit antenna, 1 receive antenna system, right? Because we basically have a wire between the two at such high rate, we may as well just beamform. Okay, so this is optimal. This is clearly capacity for this case. We can't do better than that because it's basically allowing full control of 2 antennas. The second interesting case is what happens if D goes to 1? What happens if D goes to 1? Well, let's look at it. If D goes to 1, the relay is right on top of the destination, and we're forcing it to decode everything. So if you think about that, that should mean we may as well shut the relay off, because if the relay can decode, so can the destination, and that's what should come out. So let's see if that happens. Well, if D goes to 1, even here already, what's the best rho to choose? 0, right? Right. So best rho is equal to 0. And let's see what happens here. If d goes to 1, oh, this blows up. Right? And so this is the defining bound is the first one. So yeah, indeed we get rate df is equal 1/2 log of 1 plus p1, 1 plus p1, right? Which says that we may as well not use the relay. Right, so this decode and forward method is not very useful. It's most useful when the relay is close to the source. If you think about that with the classic multi-hop, it should resonate, because if we're really close, we can just pump a lot of information to the relay over a short period of time, and then use the rest of the period to send full beamformed information, right? But that's usually not how multi-hop is done, right? Usually multi-hop is done in 2 phases. That's the wrong approach. You should do it, of course, by optimizing the timing depending on the distance. Meanwhile, this method doesn't help at all if the relay is on top of the destination. Is this the capacity for that case, if d equals 1? What do you think? Do you think you could do better than that? Well, think about what I just said. If the relay is close to the source, we can just pump a lot of information in a very small amount of time. Well, what can happen here? Well, the relay could pump a lot of information to the destination. In fact, it could pump all the information it saw by, say, quantizing its channel outputs. And since the rate is so high, it may as well send. And actually, we should be able to get the same rates as a single transmit antenna to receive antennas. Right? If you think about that for a moment. Right? Because if the relay is really close to the destination, just for a short period of time, finally quantize your channel outputs and send them all to the receiver. The receiver takes its own outputs plus the observation from the relay, does maximal ratio combining, and can get two receive antenna performance. So this kind of method is the one we'll discuss last. It's called quantize forward. Okay, it's a very different strategy in style and nature than the decode forward. Okay, so the decode forward is good when the relay is close to the source, but it's not good if the relay is close to the destination. So this is an important insight. When relays are clustered around, when relays are receiving, are near the receiver, they shouldn't be decoding, because otherwise you're not helping, right? The way to help a receiver when you're clustered around them is to quantize your outputs and send them to the receiver, who can then operate as a full antenna array. Whereas if the relays that are clustered around the source node, if we have a cluster of source here, they should all share information, send using MIMO. The nodes here clustered around, what they should all do is quantize, send them all to one person who can then decode everything, and then finally we get a MIMO communication rate. Okay, that's the insight we get out of this. So this kind of insight was first developed in around 2001 or 2. It sort of followed on the Gupta-Kumar paper, just as ideas. And for the scaling laws for large networks that used exactly that concept to get the certain improved scaling laws over the Gupta-Kumar rates with RUDAN, it could be made linear exactly using that insight. That insight was developed with Michael Gaspar. He did an internship at Bell Labs in 2001, and we were trying to understand the compressed forward scheme of Covert-Thomas, and then realized, oh, that's what it's useful for, or what we think it was useful for many antennas. Okay. Anything else to be said? Let me draw a picture. I don't have the computer with me, but it's okay, because it's more the cartoon that we'll get is important. So let me plot that here. So I'm just going to draw a little bit of a plot. So suppose this is 0, suppose this is 1, here's the source, here's the destination, and what this axis shows is the where the position of the relay, and here we'll plot the rates that we get. And so suppose here, when the relay is on top of the source, we get this, rate here. When the relay is on top of the destination, we might get this rate here. Then it turns out, so this is 1/2 log 1 plus P1. This is the higher rate that you see here. And then the decode forward rate behaves something like this. It has a peak, and interestingly, the peak in the rate is not at 1/2. It appears earlier, and this has to do with that we're using full duplex communication, and because of the correlation we get, so that we get a peak, and then it comes down pretty fast and gets worse. Why does it get worse? Well, because we're forcing the relay to decode even though it's further away from the destination. Okay? So this is what approximately the decode forward rate looks like. Now this brings up also the question of what about an upper bound on the rates? What about an upper bound on the rates? Well, an upper bound on the rates is the cut set bound. So let's just develop that quickly so that we have something to compare with. We have, I think I've drawn that a few times, but let's do 1, 2, the relay, and 3. So there's, of course, 2 cuts to worry about. And the cut set bound will say the following. The capacity is up less than or equal to the max. And the minimization is this cut has the mutual information between x1 and the 2 outputs on the other side, y2, y3, given x2. And this cut here has I x1, x2, y3. So you'll see that this looks very similar to the decode forward rate, right? The only difference being is that, this should be 2. The only difference is this y3, right? The fact that that y3 wasn't there for decode forward. And then here we can maximize overall joint distributions. Okay, so let's prove this cut set bound. It's not too hard to prove, so we may as well prove it. Oh, well, it's time for a break anyway. I just see we're already at 4. So let me prove this cut set bound afterwards, and then we'll see what changes here in the cut set bound, and then we'll plot it, right? What we do know, even before we go, is that the cut set bound must touch right here, right? Because we know that this point, well, we don't know that yet, but what we'll see is that the cut set bound will touch here. And it will touch that red curve only in one place, exactly at that red point. Okay? And the cut set bound we'll see also, well, we'll have to see. It won't touch this one, because as we talked about, we can get a higher rate than, but it will touch this curve at the one transmit, 2 receive antenna rate, which is somewhere here. It'll be somewhere lower than this rate, but anyway, it'll be here somewhere. So we'll see what those look like. That we know. So here we know this decode forward is suboptimal. Oh, and by the way, multi-hop with with free space attenuation coefficient always does worse than having no relay. So if this is having no relay, right, multi-hop does something like, I don't know, it goes something, I think it's something on this, it's something like this. That's really bad because the pre-log we're losing, right? So classic multi-hop, if attenuation exponent is 2, is bad. Of course, if attenuation exponent goes up 3, 4, right, the loss factor you're getting, like what I mean by that is, you know, having x1 d to the power of alpha over 2. As the attenuation exponent goes up, then you do better than because now you really need to do the range extension. You need to use the relay for, but so in other words, the pre-log becomes less important than the power gain that you're getting. So it depends on the situation, but for very low attenuation, the pre-log just hits you too hard that you're losing through the time sharing. So losing those degrees of freedom plays a much more important role. And also to high SNR, that always plays an important role. So that's why doing full duplex is quite useful, especially at high SNR. You're not losing degrees of freedom. Those are rate losses. So anyway, so we'll continue that just after the break.